8.2 is about comparing two means. So similar to 8.1, we're going to be looking at two different groups, or a way we can divide up people, or whatever it might be. So whether this is men and women, Republican, Democrat, however we might look and compare two groups, old treatment, new treatment. But the big difference here, unlike 8.1, where we were looking at a categorical variable, something that was yes and no, where we could make a proportion, now we're dealing with a quantitative variable. So how many pounds did they lose if they were in group A versus group B, right? That would have a numeric measurement. And in that case, the best thing to do compared to quantitatives is to compare one mean to another mean. So the mean for the first group versus the mean for the second group. So here we're dealing with quantitative data. Still with the two groups though. So again, just like before, we have a lot of stuff, but the piece we care about the most, what we're actually comparing, a true mean and a true mean to each other, one from the first group, one for the second. We have the same assumptions as before. We still need to have random assignment and or independent samples. And then our rule of thumb, well, our N1 and N2 need to be at least 30. So this is, or we could have normally distributed data in the first place. So same stuff we saw for a single mean. We're just now, every rule we had for a single mean has to be true for each of the two groups in our comparison. When we were in class, we talked a little bit about the hypothesis testing piece here. Same 5 steps. Again, we have our hypotheses. Again, I like to work in the first setting, but we could also be talking about differences because technically we know the distribution for a difference. We still have a test statistic we could calculate, but we're going to be doing this using technology. Now our test statistic, the only thing I would note here, our test statistic is a t. So because we don't have the true population standard deviation, we are going to be doing a 2-sample t-test. And then our p-values, all of that works the same. And this part we talked about in class was this idea of pooled variance. Pooled variance means you need this assumption that the variances are the same, which is a really hard assumption to prove. In fact, it's impossible to prove. And it's a big assumption to make. So most of the time, it just makes sense to not pool. And that way, whatever you get out, even if the variances are the same, it still works, but you don't have that assumption. So I would just always use the unpooled variance example from above. So we're going to go through some examples because I skipped these when we were in class. So the first exercise here says the average amount of time that boys and girls spend playing sports each day is believed to be the same. We collect some data and we get this table below. Is there a difference? All right, so the first step is the step I want you guys to be able to do, right? Set up our hypotheses. So if I were you, I'd take a moment, pause the video, set it up. So our null hypothesis is that the average amount of time a boy spends playing, I guess I'll do girls first, a girl spends playing sports per day is the same as the average amount of time a boy spends playing sports each day. And an alternative, doesn't matter what we believe personally, all we want to know is there a difference or not? There's no direction here. So is the mean for boys, I keep forgetting I'm starting with girls, girls different than the mean for boys? And we can see we have a bunch of information to help us out. We've been given the sample size, our n, we have the x bar, the average for each of those groups, and we have our sample standard deviation, our s. So we got all of these pieces. Now, steps 2 and 3 are something I said that we should be able to do with technology, right, given to us on the test. So I'm going to bust out StatCrunch to calculate these for us. So in StatCrunch, oh my God, it's being so slow. I'll pause you guys again until it finally loads. Woohoo! All right, so in StatCrunch, we're doing a t-stat, right? That was our test statistic was a t. We have 2 samples, and we don't have the raw data. We don't have each boy and how much time they spend on sports and each girl and how much time they spend on sports. So we're going to do with summary because we actually have the values. And you can see here right away it asks us for the mean, the standard deviation, and our sample size, which is exactly the information that was given to us in our table. Sorry, I'm looking for a part 8 so I don't have to flip back to my thing. Hold on. So our given values. The first sample, I'm just going to go ahead and call this the girls because they were the first in our ordering, and it doesn't matter. The first sample had a mean of 2. They spent 2 hours a week on activities or sports, whatever this question's about. They had a sample standard deviation of 0.8667. And their sample size was very small. We only had 9 girls sampled. The boys, on the other hand, they spent an average of 3.2 hours playing sports. They had a standard deviation of 1.00. I don't need the 0.00. I don't know why I'm writing it. And then there were 16 of them. So unfortunately, StatCrunch always has a default to pool variances, so we're going to take that off. We have that 0.8667 and 1, and we don't know that those are the same or close enough to pool. So I'm going to uncheck that. We're doing a hypothesis test. We want to say that there's no difference as our null, and that there is some difference as our alternative. So you can go ahead and compute. And you can see here, the actual difference between the boys and girls was 1.2 hours. The standard error, the actual calculation that we did not do, is here. The degree of freedom, you can actually see, if we go back to part 8, the standard error they talked about was this calculation for us. The degree of freedom, when you do this in an intro stats book, they tell you to just use the smaller of the n minus, like of the 2 sample sizes, minus 1. But it's superly overly simplistic. Calculators and computers will come up with a different or correct degree of freedom. So this already points out why it does not make sense to do this by hand at all, considering we are unable to get the true degree of freedom. In fact, I'm going to go ahead and Google it so we can see how gross that degree of freedom formula is. All right, so I know you guys don't care, but I force you to do this anyways. So here in this example, the degree of freedom calculation, they actually use a capital N for the sample size, which is very strange. But the actual degree of freedom that is in our StatCrunch output for this t-test, this is how it's calculated. So you can see that that is a monstrous calculation to do, which is why we don't do that, and we're just going to use technology to do this. So the only 2 pieces that we really care about here are test statistic and our p-value, right? So our test statistic is negative 3.14, and our p-value 0.0054. So we'll bring those back to our example. So our test statistic, this was t is equal to negative 3.14, and our p-value 0.0054. Now the pieces I actually want you to be able to do after you get this, make our decision, write this up in a sentence. So because our p-value is less than an alpha 0.05, which they told us to test with, right? We're going to reject the null, which means there is enough evidence to conclude that there is a difference in the average amount of time boys and girls play sports each day. And I'm going to be lazy and not write out that sentence, but you guys see the sentence up there. It is important in this sentence that we have the word difference, because that's what our hypothesis test is about, that we have the word, even more importantly, that we have the word average in there, or mean, something to say that this is a test for means, and then the context that we were talking about.